G'day viewers. In this segment we're going to begin our exploration of the physical layer, starting with an overview. Here's a reminder of where we are in the course. In the introduction we went through protocols and the layering mechanism, which produces stacks like this shown in the diagram. Now we're going to work our way up through the physical layer towards the application layer. And we're just at the very beginning of that process. So let's just talk a little bit about the physical layer. The physical layer concerns itself with how to send bits of messages across a link. Now the difficult issue here is that we would like to think of the link as taking bits in one end and providing bits out the other end. But that's not how links work. Links and other kinds of media carry analog signals, such as that shown in the middle here. So we're going to need to work out how to convey bits of information using analog signals. To do that, we're going to go through several different topics. First, I'm going to tell you about the different kinds of media, including wires, wireless and fiber optic cables. Then we're going to talk about how signals propagate over those media and see the different effects of bandwidth, attenuation and noise. Finally, we'll move on to the key issue, which is really different modulation schemes, or how we represent bits using different signals. And then to wrap up the area, I'll talk about some fundamental limits which are known. Real engineered systems will need to operate within these limits. At the end of our exploration of the physical layer, we'll have a simple model of how links operate. That will give us an abstraction for a physical channel, and we'll only need to think about this abstraction from then on. I'm going to show you the abstraction right now, and then for the remaining lectures in this week, we'll work up to it. Well, once we're done with links, we'll represent them fairly simply using a couple of key parameters here. You can see that the link is drawn here. It goes from one end to another end. And there are only really two parameters which really matter here. One is the rate R, and that is the information carrying capacity of this link, sometimes called the bandwidth, the capacity, or the speed. It's measured in the number of bits per second you can send. The other key parameter is the delay in seconds, which is how long it takes for information to cross the link. It's related to the length of the link. And in particular, signals propagate along the link at roughly 2/3 of the speed of light, 2/3 of c. The speed of light, c, is the speed at which electromagnetic signals propagate in free space. In media like wire, they propagate at roughly 2/3 of that speed. Once we have these link parameters, then we'll simply send messages down the link. There are a couple of other properties which will become important later. Some channels are broadcast, so that when you send the signal, it's delivered to multiple receivers. It's broadcast to those receivers. And we'll also care about the error rate to know whether links often deliver messages reliably or whether their messages are often delivered in error. Once we have that model, we can do a few exciting things with it. Here's one application of it. We can calculate the latency with which messages are sent. Now the latency is simply the delay to send a message over a wire. From our model, there are really two different components here. One component is the transmission delay. That's the time to put an M-bit message on the wire. Well, the transmission delay is just equal to the message length in bits divided by the transmission rate. The second component is the time it takes for the bits to cross the wire. Now that propagation delay, that was really what we were given as d. The propagation delay is equal to the length divided by 2/3 of the speed of light, because that's how fast signals propagate. Putting these all together, we have that the latency of the time taken for a message to cross a link is simply the sum of these two terms. It's really m divided by r plus d. And that's the formula for the latency of a message. And here's that same slide, just cleaned up a little bit so you can see everything. Now before we go any further with the calculations, let me just remind you of some of the metric units that we're using. They're given in this table here, the main prefixes. We'll use the prefixes kilo, mega and giga to mean thousands, millions and billions, and similarly m, micro and n for nano to represent thousandths, millionths and billions. We'll generally stick with powers of 10 for rates, just to make all of the math simple, although we'll use powers of 2 for storage when we're strictly just speaking about storage. So 1 megabit per second is simply 1 million bits per second. whereas 1 kilobyte is 2 to the 10 bytes, or 1024 bytes. And you'll also occasionally see a capital B for bytes and a lowercase b for bits. Okay, now let's go through a couple of latency examples. Here are two different scenarios for us. The first is our dial-up scenario. This is just using an old-fashioned telephone modem. You might imagine here that the delay is quite short. The telephone modem is going to some other computer in the same city, say. The rate is quite low. It's 56 kilobits per second, low by modern standards. So let's compute our latency. Our latency, well, let's just add the delay because that's easy. It's going to be 5 milliseconds plus the message in bits, that's 1250 times 8, times the rate, that's 56 kilobits per second, so that's 56 times 10 to the 3, and that's equal to, if you can do that sum, you'll find it's about, 184 milliseconds. Okay, you need a calculator to do that sum maybe. But the interesting part here is that this second term really dominates. Nearly all of the latency comes from the amount of time to put messages on the wire. Second example, broadband. You're sending a link across information across country. Here the delay is going to be larger. Let's just call it 50 milliseconds would be reasonable. You're also using a much faster link. 10 megabits per second would be a good, decent broadband. Let's do our calculation again. The latency is equal to 50 plus, we have the same message in bits, 1250 by 8 times 10 megabits per second, that's 10 by 10 to the 6, and I'll tell you that's equal to about 51 milliseconds. In this case, all of the latency came from the propagation delay. The transmission delay contributed very little. Okay, let me clean this up. And you can see here, the point that I want to illustrate is that you can obtain relatively high latency from either a long link or a slow rate. In fact, for many links, often one of these two components, either the transmission delay or the propagation delay, will dominate. And in that case, we'll generally just simplify our latency calculations and use one of them. For rates above a megabit per second, for instance, anything 10 megabits per second or so forth, usually the transmission delay is very small and we don't worry about it. We can also use our simple message model for other applications. Here's another one, the bandwidth delay product. Now, it's interesting to observe that messages actually take up space on the wire. Since when you transmit the signal, it's not delivered instantaneously, some portion of the message is actually stored inside the network. The bandwidth delay product, written here as BD, is the measure of the amount of data that's in flight and hence stored inside the network. The bandwidth delay product is simply, literally, the bandwidth times the delay. It's the product. You can measure it in bits or in messages. It's going to tend to be small for local area networks where, for instance, the delay is very short. To get a high bandwidth delay product, you really need both of these terms to be reasonably high. So we're looking at fast networks that go for a long way. These are sometimes called long fat pipes. Okay, let's see an example. You're using fiber at home and sending the information across the country. You've got 40 megabit per second, nice decent fiber connection, and our latency, our propagation delay, will be 50 milliseconds to cross the country. So the bandwidth delay product, let's see, 40 by 10 to the 6 times 50 by 10 to the minus 3. Let's see, that's 2000 by 10 to the 3. This will be in bits per second, so if we just divide by 8, that's going to be 250 kilobytes. That's actually quite a lot of information. Basically, you could store an entire book inside the network here while it's in flight. It's quite amazing. Okay, here's that slide cleaned up again, and we're done for this example.